the first of our advanced considerations about scheduling is the idle task. And sometimes the scheduling algorithm cannot produce a new process to run next because there is, quite frankly, nothing to do. Right? No process is running that wants the CPU right now. So what do we do in that situation? We need something, right? And for that, operating systems have an idle thread or idle task, however you want to call it. And the purpose of the idle task is more or less to fill up time that's otherwise unused. The actual implementation of the idle thread can vary across different systems. In some cases, you just invoke the scheduler repeatedly, hoping this time we'll come up with a different result. In others, it just does a bunch of useless addition. It might be a whole bunch of no-op instructions. With truly nothing to do, the CPU can maybe be told to halt or switch to a low-power state. Whatever it actually does, the idle thread never has any dependencies on anything else. It's always ready to run. It cannot get blocked because such a thing is just not possible, right? That's a key defining factor of the idle thread, is that it's not possible for it to get blocked because it's always ready to run. Okay, so if it doesn't do anything, why is it there? Why is it there? Well, here's a few hints. Number one is it prevents having special cases in the scheduler. You don't have to have any code that covers the situation of what if the returned result is empty from the task that we should schedule next, because, well, having the idle task means there's always something, even if that something does nothing. It's also good because we can look at the runtime that is assigned to the idle task, and that gives us some accounting information about how much of the time the CPU is not doing anything useful, right? It's not running a user program or not running some operating system task or something like that, which is fine. In fact, a lot of the time, what you want on your desktop or your laptop is for Task Manager or equivalent to tell you that the system idle process or another idle task is taking up a large percentage of the CPU. That means the CPU is not doing anything. It doesn't mean that some internal system utility is using up all your time. There was an actual technology journalist named John Dvorak who wrote an article complaining about system idle task using up all of his CPU, and he didn't understand why. And oh boy, not a good look for him. Not a good look at all. And of course, saving power by shutting down parts of the processor it seems like a nice savings of energy and potentially increases the battery life of your device. So in a lot of circumstances, you want that. But on the other hand, time when the CPU is not doing anything might potentially be put to use somehow. Are there chores that we could be doing that the operating system could do? Could we be collecting or compiling some statistical data? Could we do some work cleaning up disk storage? All of those things are opportunities to make use of what is otherwise dead time. And yeah, as I say, that whether or not you want to do those things probably depends on are you on battery or not, right? You don't want to do a whole bunch of extra work on battery because it's just killing the user's battery and making them sad. I know, why does my laptop not live as long? But if you're plugged in on power and it's overnight, why not? The next big consideration that we want to talk about is called priority inversion. We're in the upside down. And this is a situation that we get into when a high priority process is blocked and waiting for a low priority process, right? P1 is a high priority process and it's blocked on a semaphore while process P2 is in a critical section. Because P2 is a low priority process, it might be a long time before it's selected to run again and can finish and exit the critical section, which is frustrating, right? Our high priority task is waiting for a low priority task, and that's not something that we would like to see. It may be unavoidable, but it's undesirable, right? And this is frustrating, right? P1 can't run, it's blocked. Fine. In the meantime, some other process, P3, that has a lower priority than P1, but say higher than P2, carries on execution, and this isn't helping process P1 to run, which is something that should happen. So what do we do? The solution is called priority inheritance. Now you probably get what I was talking about how some processes are more important than others, owing only to inheritance, which doesn't seem fair. But priority inheritance is what we're talking about. And that is, we increase the priority of P2 temporarily to be equal to that of P1 so that P1 can be unblocked as quickly as possible. And that is to say, a lower priority process should inherit the higher priority if a higher priority process is waiting for some resource that the lower priority process is holding. So that means P2 gets selected, can execute, exit the critical section, and then its priority goes back to normal, meaning P1 will be selected and may then continue execution. And a famous case of priority inversion took place on the Mars Pathfinder rover, pictured here. In short, a low priority task would acquire a semaphore locking the information bus, and a high priority task also needed the bus. There was finally a medium priority task for communication, which ran for a long time. And if a low priority task had the bus, the high priority task was blocked. The communication task at medium priority would be selected to run. And while that happened, the low priority task would not finish and would not release the semaphore. Accordingly, the high priority task was stuck waiting, and after a specified period of time, the system would assume that the high priority task's failure to complete its work meant it was stuck, and its deadlock resolution strategy was the one we call Armageddon, which is a total system reboot. And total system reboot meant loss of some data that had not been appropriately saved or transmitted back to Earth. So the Pathfinder solution was to enable priority inheritance on the information bus semaphore. That meant that the low priority task would get a higher priority than the communication task. It would run to completion, and then the system wouldn't be assuming that a deadlock had occurred. It was quite fortunate, I will say, that this option was built into the system already at the time that the thing was built and launched and sent to Mars. It only needed to be turned on, right? It didn't have to be implemented from scratch. Doing a major software update on a system that's located literally on another planet is not quite the same as installing Windows updates on Patch Tuesday. We're also going to talk about multiprocessor scheduling. And multiprocessor scheduling is going to be a step up in complexity as compared to what we've talked about previously, and the complexity does increase somewhat dramatically. And there are three kinds of multiprocessor systems that we could consider realistically. The first is a distributed system, and we have a collection of relatively autonomous systems that interact. For more about this, there is a technical elective, at least the ECE one. I don't know if there's like a CS equivalent. It is ECE 454, and it is distributed systems. Of course, distributed systems are beyond the scope of what we want to talk about here. And then there are functionally specialized systems. And the system has specialized chips that work on their specific area. So there's a hardware controller, and it has its own scheduling. We're going to come back to that a little bit when we talk about I/O scheduling in a future topic, but it's not something we're going to consider right now. And then finally, there is tightly coupled, and that is our focus. This is a set of processors that share a common main memory and are under the control of the operating system. And that's the thing we should be most familiar with from everyday experience, but it's what we care about in this topic. And then we have to worry about the interactions of various processes, right? How often do the various threads that are running interact? There is very fine-grained, which is interactions within a single instruction stream. There's medium, which is interactions within a single application. There's coarse, which is distributed across multiple processes. Very coarse, which is distributed computing. And for completeness, there's the unrelated processes. So they don't interact at all. They just happen to be running on the same system. And some estimates are provided in the rightmost column. saying how often do these things interact, right? If we are taking different processes and having them run on different CPUs, they may interact, every 200 to 2,000 instructions, and that's probably not a big deal. But if we are looking at taking a single instruction stream and splitting it up across multiple CPUs, a lot of care and attention needs to be given to make sure that we get the right answer, right? We need to ensure that we get the same answer that we would get if everything was running sequentially. So you can imagine, if you will, just how big of a headache this might be. So asymmetric multiprocessing, incidentally, is something I'll mention, but it's not something that we're going to spend a lot of time on. But asymmetric multiprocessing used to be the model in some systems. And it says there is one boss. It's usually CPU 0, but it hypothetically could be any of them. And this processor and this one alone is responsible for assigning work and managing the kernel data structures. And it is, like I say, the boss. It gives the work, and the workers do the work that they're assigned. Much more common is symmetric multiprocessing, also called SMP, if you've seen that abbreviation before. And in that one, each processor is responsible for scheduling itself, right? That's a bit more complicated to manage to some extent, because we need to make use of mutual exclusion and other synchronization techniques in the kernel to make sure that everything works the way it's supposed to work. We don't want to have two processors trying to dequeue something from the ready queue at the same time. Only one of them should take the task out of the ready queue and do it. But overall, it is a manageable amount of complexity. We've learned enough of the tools that we need to actually make it work. It's, as I say, not magic. Work does have to take place to make it happen, but we are going to do it. Whether we have asymmetric or symmetric multiprocessing is as much about the operating system as it is the underlying hardware. As I recall, there were some systems, I think it might have been Solaris, where like one version of the operating system used asymmetric multiprocessing, and then a later version used symmetric, or vice versa. I don't know. This is obscure enough that I don't recall it off the cuff, but we're going to talk about symmetric multiprocessing. Now, when we have different processors, they may or may not have their own cache. And if we talk about an x86 kind of CPU, it is the case that every processor has some of its own independent cache and some shared cache. And that presents some slight headaches for us. So in an x86 type system, like level 1 and level 2 cache are per processor, but level 3 is, say, shared between all of them. But let's imagine, just for the sake of the discussion, that it is just one CPU has its own level 1, level 2, level 3 caches. Okay, so if that's the case, well, things require, for maximum efficiency, if you will, processor affinity. And processor affinity is just saying, like, you are literally my favorite CPU. A process has its data in the cache of that processor. So if process A is running on CPU 2, a bunch of its pages are in the level 1 and level 2 cache for that CPU. And if we move it to another processor, all the data is in the wrong, quotation marks, cache, and there will be more cache misses than if they stayed executing on the same CPU. And this is referred to as CPU affinity, the desire to stick with a given processor, right? This is where my stuff is. I would rather be here. Now, if the operating system is going to make an effort but not guarantee that a process runs on a given processor, it's called soft affinity. Right? It can move from one processor to another, but it won't do so if it can avoid it, to reduce the number of cache misses. And some calculation will necessarily take place to figure out when does it make sense. Right? If we're going to be waiting a long time for our favorite CPU, it doesn't make sense to wait. We'll just go and take the cache misses. It's worth our while. But if the wait is short, it might make more sense to run on the CPU that we like, that has our data in the cache, because, well, that's just better than just better than having cache misses that we could otherwise avoid. Okay. The alternative, and Linux offers this as well, is hard affinity, where we can specify that a process will only run on a processor or group of processors. It is an option. It is something that is configurable, and as a user you can set this kind of thing if you insist. As per usual, I'm a little bit skeptical that users make good decisions about this kind of thing, because it does seem like something that's easy to get wrong, but you can do it if you want. And it makes sense in some certain server configurations where you want to say, okay, this process is guaranteed to have exclusive access to its CPU, and another process is guaranteed to have exclusive access to its CPU, and therefore we have some reassurance, if you will, that the processes don't interfere with one another. Another reason why we might be interested in this is non-uniform memory access. And up until now, we always think about memory reads taking an equal amount of time no matter where they are. But that's not always true. If we have one bus connecting the CPU chip to all of main memory, it's a reasonably safe assumption that we have uniform memory access. But if the CPU can access some parts of memory faster than others, then what we actually face is non-uniform memory access. This isn't so much a thing these days, right? If you build a PC, a desktop PC, you put one chip and the chip has 6, 8, 14 cores, whatever it is, and you put a couple of RAM sticks and that's it. But going back 20, 25 years ago, you could have a multi-processor system where you had 2 chips and each chip had its own bank of RAM. And that looked more like this, where you had non-uniform memory access, where there is memory that's associated with each CPU, and it's not inaccessible from the other CPU, but the access is slower. It has to travel across a different bus and takes more time and all of that. And if we do have this situation, then we should make an effort to assign, say, a process whose memory is in the left bank of memory to the CPU that's closest, because the execution there would be faster. And the memory allocation routine should also pay attention to where to allocate memory requests, preferring to keep program code together in memory. So there's a part to play for each of those things. Yeah, if we get it wrong, if memory is in the wrong place from the CPU's perspective, or the CPU is in the wrong place from memory's perspective, they're both kind of equivalent, it doesn't mean game over, it just slows down execution. So if we want to do things as quickly as possible, that's something we prefer to avoid. And then this idea that I touched on earlier about processor affinity also leads us in a way to the subject of load balancing. And it's presumably obvious that if we have 4 processors, it's less than ideal to have one processor maxed out with a queue of things waiting and have 3 other processors sitting around doing nothing. We want to keep the workload balanced between all of the different systems, and the process for this is load balancing. And load balancing is typically only necessary where each processor has its own private queue of processes to run. If there's a common ready queue, then to a certain extent, load balancing happens all on its own. If everyone is dequeuing from the common ready queue, a processor with nothing to do will just take the next process from the queue and go from there. This resembles, if you will, the bank queue waiting model, where everybody is in one single line or queue at the bank, and when you get to the front of the queue, whichever teller is ready calls you forward. That's distinct from, say, a supermarket model where there are different checkout lanes, and you choose which checkout lane to wait in, and you could choose wrong, right? Most of the modern operating systems we're familiar with do have a private queue per processor, so there is going to be some load balancing, which is to say moving of tasks from one place to the other to hopefully get things done faster. And there are 2 non-exclusive approaches, which is to say non-exclusive in this case means we could do both of them. We don't have to do only one. And push migration says, well, a task run by the operating system periodically checks how busy each processor is and then moves processes around to balance things out, which is within some tolerance, right? It's never going to be completely even, and we're never entirely sure how long processes are going to take, but if we can see there's a queue here and there's nothing there, well, we know what to do. Pull migration, on the other hand, is when a processor with nothing to do steals, and I say steals in quotation marks, a process from the queue of a processor that is otherwise busy. And the Linux and FreeBSD schedulers use both. As you can imagine, this conflicts with processor affinity. If a process has a hard affinity for a processor, we can't move it. That would be breaking the rules. If there's a soft affinity, we can move it, but it's not our first choice, and we'll do it only if there's sort of no other option. And should we always move a process, despite the fact that it means cache misses? Should we never do so and leave processors idle? There's no obvious one-size-fits-all answer. Maybe in doing the calculation, we can put a penalty on moving and only make the move if we think that the benefit exceeds this penalty. But again, those penalties are guesses. It's not easy to know exactly what the penalty will be. So, yeah, it's an interesting question. And finally, I want to also talk about multi-core processors. And before the early 2000s, realistically, the only way to get multiple processors in the system was to have multiple physical chips. But if you open your laptop or you've built a desktop, you probably have only one physical chip. And why does this work? Well, it's because the chip you buy now has multiple cores. And as far as the operating system is concerned, a quad-core chip, just as an example, is made of 4 logical processors. And it doesn't really matter, right? From the point of view of the operating system, whether the underlying hardware is multiple chips or multiple cores inside one chip, these are units to which we can assign work and work will get done. So on a cache miss, as we've discussed more than once now, CPU core can spend a lot of time waiting for that read to take place. And so we might refer to periods of time where there's computation as compute cycle and time spent waiting for memory as a memory stall. Why a stall? Because we can't move forward, we're waiting for memory. And this tends to alternate. We'll do some stuff, we'll have a cache miss, we'll wait, we'll get what we need, and then we can continue, but there will again, at some point in the future, be another cache miss, and we'll get stuck again. And these tend to alternate, and how often they alternate and how long they last and all that is, of course, entirely dependent on the nature of the cache misses and how long it takes to resolve them and how much computing we do before the next read. But these things are like manageable in terms of measuring them. So we end up with something like this, right? The diagram is a little bit ridiculous. The compute cycles and memory stall cycles don't alternate perfectly evenly sized boxes, but you get the idea. And during a memory stall, we're looking for something to do. If you take a course on processor design or even compiler design, and or in programming for performance, we might talk about the idea of moving instructions around so the memory read goes out early and some other instructions can get executed in the meantime, because we want to start things sooner rather than later to reduce the amount of time that we're waiting. But there is another solution. This other solution is originally called HyperThreading, or at least that's what Intel called it. Whether you want to call it something else is kind of up to you. And what we're going to do is assign 2 threads to each core. Each thread is running independently, and from the point of view of the operating system, it's treated as if there are 2 cores. But if one thread does a memory access or stalls, the code can switch to the other thread that's ready with a limited penalty. So picture, if you will, you're working on 2 assignments, and you have 2 pieces of paper. Let's imagine one of them is a math assignment, and the other is a physics assignment. Pretend it's 1A. right? And you're doing them on pieces of paper because it's easier to write the formula that way. And what you're doing is basically you have two things open at once, and you can say, well, all right, if I get stuck on the first one for some reason, I don't have to post a question on Piazza and ask for clarification. While I wait for the clarification, I'll just switch to the other thing that I already have open, and we lose less time that way. Right? By having something that's already open, having something that's already ready, we don't have to do the work of like, all right, figuring out what we're going to do next. So we're switching with a limited penalty. And the first CPU I had with HyperThreading was like, at this point, 20 years ago. It had one physical core, and it would seemingly work on two things at the same time. It doesn't really in the strictest sense. And the performance is not double that of having just one CPU, but it is still an improvement over having just one. And so the goal of hyperthreading is to do something like this, right? If we have thread 0 that's executing, when we get a memory stall, we can switch very quickly to the other thread that's sitting around and waiting for us. And when that's the case, then we just pick it up and go with it. And it will eventually at some point also get a memory stall, in which case, all right, we know what to do. We'll switch back to the other thread if it's ready. Reality is, of course, not always this tidy. There is certainly the possibility that we have nothing else that's ready at a moment, or that the memory stall happens on thread 1 very quickly, in which case both of them are in a memory stall, and it's the diagram is kind of comical for sort of how it's very optimistic, if you will, about how it should work. But in a reasonable case scenario, we will actually accomplish more work than we would if we were just executing the one thread at a time. So there is, incidentally, then, some benefit. If we have coarse-grained multithreading, we potentially have to flush the entire instruction pipeline, where we are basically looking for something completely new to do, and whatever steps we've done in the pipeline have to be thrown away, and they'll eventually be redone, but it could be quite a while before that happens. And the thing is, when we talk about the instruction pipeline, using the simple model we've talked about, where the instructions are like fetch, decode, operands, execute, that we might throw away, it doesn't seem that bad. But the Intel CPUs of the time had fairly long instruction pipelines, like 30 cycles or something like that. So flushing it was actually kind of more painful and more expensive than we might imagine from the simple CPU model. So with that said, switching between two threads within the same pipeline is actually more beneficial, because it does reduce the amount of work that's necessary every time that we are switching. So it turns out we can have more than one level of scheduling in the system, right? We have assigning a process or a thread to a particular processor to execute, and then within the hardware itself, there will be potentially some back and forth switching between the different threads that are running inside the CPU core itself. Okay, so that concludes kind of our theoretical discussion of the complexities of scheduling. We'll talk next about actual scheduling algorithms that are used in real operating systems, the Windows and Linux kind of scheduling.